Hello, and welcome to this presentation on quality assurance and quality control for water quality monitoring programs. My name is Eric Hosteen, and I'm a product manager with the Hydromet group that makes HydroLab water quality instruments and OTT water quantity instruments. First, we need to establish what we're talking about when we say QA/QC. QA/QC is an acronym standing for Quality Assurance and Quality Control. Various organizations and authorities on quality publish definitions of quality assurance and quality control that are not always clear. What we have on this screen are one definition of quality assurance and quality control, both that are derivatives of something taken from Wikipedia. Quality assurance is the planned, systematic processes that provide confidence in a measurement process's ability to achieve its intended outcome. Quality control are activities that focus on finding defects in specific elements of the measurement process. For today's discussion, the nuances between quality assurance and quality control are not important. What it really comes down to is that any endeavor where the goal is to confirm quality can be considered QA/QC. This is what we'll focus on. What are some guidelines and best practices that should be followed to give users of water quality instruments and the data they generate confidence in the results? While we'll be talking in context of water quality instrumentation, many of the points can be carried over to any program involving measurements, such as water level, discharge, or precipitation measurements. Sometimes it's useful to draw upon examples from everyday life to drive home a point. While QA/QC is probably something most people associate only with their professional life, it's really all around us. Here's an example. How many think to question the accuracy of the fuel pumps at the gas station or the scales used to weigh food products sold at a market? Most don't bother. It's common for governments to mandate inspections and certifications of measurement devices used in commerce. These programs are based on defined processes and systems so that buyers and sellers can feel comfortable that their transactions are fair. So when it comes to monitoring water resources, how can the stakeholders be sure that the measured values are representative of the truth? The answer is QA/QC. So how do we know a gallon or liter of gas is really that? Or how do we know what a pound or a kilogram of vegetables is? Somewhere along the way, this needed to be established. Taking these questions seriously, it's easy to go down a path with no end. How can someone be absolutely certain that the gas pump delivered exactly 1 gallon or the 5-pound bag of potatoes is just that? At some point, sensibility takes over and there is an agreement to take that leap of faith and call some repeatable, consistent standard the truth. The truth or true value is the reference or standard against which comparisons are made. In the water quality world, this could be another instrument that is kept maintained and out of circulation to serve as the truth. This is sometimes called a golden song. Or a sample measured by a trusted third-party lab, perhaps using an alternative measurement method, or the use of commercially available or self-made calibration standards. So for a QA/QC program, organizers need to establish and define the true value. In some cases, it will be possible to leverage standard methods or guidelines set up by a government authority. A key underlying message here is that all measurement standards, and measurements for that matter, carry uncertainty. Uncertainty in measurement is driven by sources of variation in the measurement system itself, such as human, environmental, and procedural variations. Of course, to avoid a variation, it's necessary to first identify sources of variation. Some variation is avoidable, others is not. Professional judgment needs to be applied to determine the sensible limits to variation reduction. Eliminating all sources of variation in the measurement process and outright proving data accuracy can quickly become impractical and cost prohibitive. For example, taking a grab sample from each sampling location to be analyzed by a third-party lab defeats the purpose of making measurements in situ with a field probe. On the other hand, relying solely on an instrument calibration may not be enough. Over time, evaluation of historic performance and past experiences will help users set up acceptance criteria that work for a particular monitoring program. Whether the measurement of interest is a real-time measurement, grab sample, spatial profile, or even from a laboratory-based instrument, a core element to a QA/QC program is to have a means to check the primary measurement. In this sense, the QA/QC measurement needs to support or be in alignment with the primary measurement. Generally, measurements are taken temporally, which means with reference to a specific time or sequence of time, or spatially, which means with reference to a specific location or area profile. So to have a QA/QC measurement that is in alignment with the primary measurement, it needs to be taken at the same time and place to minimize sample-to-sample variation. For example, if a field instrument is deployed, set up to collect data at an hourly interval, let's say at the top of every hour, the QA/QC measurement should be on the hour as well, not 15 or even 5 minutes before or after. Similarly, the measurement or sample needs to be taken not from 100 feet away, but at the same spot. If an instrument is deployed at a depth of 10 meters, the sample needs to be taken at a depth of 10 meters, not 8, and call it good enough. An ideal program will take QA/QC measurements simultaneously and at the same location as the primary measurement. This may seem rigid, but these guidelines should be followed as much as possible in the interest of minimizing sample-to-sample variation. A common rule of thumb for QA/QC programs is the 10% rule, where at least 10% of the effort in a sampling program should be reserved for QA/QC. Translating this to an example of a hypothetical monitoring program that looks at 10 locations in a water body, at least one should be a duplicate sample, laboratory blank, bottle blank, calibration check, or some similar activity that provides confidence in or verifies the reading. For long-term monitoring, this would be impractical. At 15-minute intervals, which is about 100 measurements per day, it would defeat the purpose of having a deployed instrument and also get 10 QA/QC measurements per day to meet the 10% guideline. The best that can be done from a practical standpoint is to take QA/QC measurements or samples at the beginning and end of each data set. Assuming a typical deployment of 30 days, 3,000 meter readings would be collected during this period, with only 2 QA/QC measurements. This is less than 0.1% effort put into QA/QC, far short of the 10% rule, but may be the best that one can do. The only check to determine the accuracy and performance of water quality instrument measurements in the field is with an independent field measurement. Field measurements should be obtained as frequently as possible to verify performance or confirm unusual occurrences that would otherwise lead one to doubt the accuracy of data. Here it's important to be practical and do what time, money, and resources allow. What may seem like a daunting amount of effort will have significant payback. All the QA/QC data can be used toward the goal of maximizing the quality of field data sets. Over time, it will become evident just how long before sensor drift and fouling will begin to have an effect on data quality. Also, it will help to determine if maintenance and calibrations have been done correctly. Step changes in data are often suspicious and sometimes can be traced back to something human-caused, perhaps a bad calibration or a missed maintenance routine. Analysis of historical data from QA/QC programs allows water resource professionals to set stricter acceptance criteria for data collected. The absence of a robust QA/QC data often leads professionals to falsely reject data that may have been okay. Groups that have good QA/QC programs generally end up rejecting less data than those groups with lax or maybe even non-existent programs. So while the effort of instituting a robust QA/QC program may be great, the payback and benefits can be substantial. One element complicating QA/QC programs is that more and more water quality instruments are being used for water monitoring programs. Testing instrument performance individually can take more time than what is available. A good way to test multiple instruments simultaneously is via tank testing. Setting up multiple instruments in the same tank can be used as an indicator of repeatability and performance among units of a group. Such an approach allows one to demonstrate that one unit is measuring within reasonable limits of the rest. For a basic tank test setup, put a submersible circulating pump at the bottom of a large tank, like the one seen in the photo in the previous slide, and fill it with water. A large garbage can often works well and is easy to find at a local hardware store. In this type of setup, 10 stons is usually the maximum number that can be tested together as a group. It's important to prepare each instrument before testing using the same methods that would be used to prepare the instrument for field use. Instruments need ample time to equilibrate with the environment before testing begins. Record measurements for all the parameters every 5 minutes for 12 to 24 hours. Afterward, graph the data by parameter, so one parameter per graph, and review the data for analysis.